It's recording. There, I did all the things. All right. So it's been a while. So we'll start with a little bit of review. I'm not going to review all the things, but just some key things. And then we'll keep going through section 2.1, which is quite large, right? It's summarizing numerical data. And there's a lot of kind of ins and outs and things to know about. And so, well, where can we start? We talked about different shapes of distributions. And I kept a slide actually that I'm gonna use later, but just in general, some key shapes for distributions are this normal distribution. So this normal distribution is technically a unimodal and symmetric distribution. Kind of combined my R and my I there, but there you go. So it's unimodal and symmetric, mode being a peak, right? And so we don't need to review that. That's stuck in there, I think. Right, so mode is a peak and unimodal means there's one peak. And today we're going to focus on just unimodal distributions. But we said, okay, I could have a distribution that looks like this, or I could have a distribution that maybe looks like this. All these are unimodal, one peak, right? But this first one is skewed to the right because it's skewed in the direction of the tail, right? And so let's make a note of that here. And this one is skewed to the left because it's skewed in the direction of the tail. So here, this one is skewed right, or right skewed, or positive skew, whichever one of those you prefer. And this one is skewed left. We're going to be relying on that today, right? The different shapes. And so another little bit of review was, okay, how do we describe a distribution? I'll say when looking at a histogram, right? Just to sprinkle that in there, histogram is the most common way that we are going to visualize numerical data. And so to describe a distribution in a histogram, we need to talk about three things, right? Imagine you're on the phone, your BFF, you're talking about, okay, how can I describe this thing? We have to talk about the shape, the center, and the spread. And the spread meaning just minimum to maximum. So to describe a distribution in a histogram, we need to discuss three things. Always really painful when I give you a question that's worth 1.5 marks, half a mark each, and I ask you to describe this distribution. That's a really easy question, but then you only talk about one of the things, so I can only give you half a mark. First is the shape. Second is the center. And the third is the spread. In terms of the shape, your options, let's boil it down. You can talk about skewed to the left, skewed to the right, or we could be even more general and say, well, is it normal or non-normal? If it's non-normal, we usually show off which direction it's skewed in, right? But that's enough for me to know kind of what it looks like. Or that's enough for you to tell me. the center is going to be wherever the peak is. So roughly where the peak is. Roughly where the peak is. And the spread is roughly minimum to maximum. These are just kind of rough ideas. You're just eyeballing it. And so just so someone knows, okay, on a scale between 10 and 100 is way different than a scale from negative 500 to 5,000, right? But it just gives us an idea of what we're looking at. So then we said, okay, roughly where the peak is roughly the minimum to the maximum, we're going to need a little bit more. And so then we built up to the numerical measures of center and spread. Right, of course, there's math to be done. One numerical measure of center is the average or the mean. So the average, which is the mean, and I'll say this is the center. And we talked about the formula for the mean, which is using summation notation usually, the sum of the xi's as I goes from 1 to n over n. Or if you're lazy like me, the sum of the x's over n. I'm just dropping that index, right? And it's just assume that you know that you have to add up all the things and divide by the number of things. So if you prefer to read it like this, you can just ignore the indices and be happy. So we used the mean and the formula for the mean to introduce summation notation, or kind of reintroduce summation notation if you've seen it before, and just show you that you already know how it works. Okay. For the spread, we started with the variance. Now the formula for the variance, you might not recall. I equals 1 to n of xi minus x bar squared divided by n minus 1. We broke down this formula, right? And so what are we doing here? From each observation in our data set, we subtract the mean, right? How far from the mean is this thing, right? Some are going to be below it, some of it are going to be above it, just by how the mean works. If you added all those up, all those deviations, right, you would get 0, again, because of how the mean works. So that's why we square it. Squaring it makes it positive. So now we're adding up all these squared deviations, right? And so that's what this summation is all about. And then we divide by n minus 1. Kind of confusing, but we just need to know that we do n minus 1 instead of n, just because it gives us a better approximation of the population variance. Whoa, okay. There. The variance is not really what we're going to be using. Most commonly in this course, we use the standard deviation, but the standard deviation is just the square root of the variance, which means it's going to be the sum from I equals 1 to n of xi minus x bar squared over n minus 1 square rooted. That's going to be on your formula sheet, so don't worry. Same with the mean. You don't need the mean on there, but you get it anyways. We introduced some notation, which I guess I'll put on the right-hand side. We use X bar for the mean. Remember, that's the sample mean, right? Versus what? Mu for the population mean, right? And so versus mu is the population mean. Yeah. So we use Greek letters typically to denote the population. Yeah. A lot of getting to know these little guys before we can do anything. So the variance is denoted by S squared versus a lowercase sigma squared. Versus sigma squared is the population variance. Remember, we're going to have these kind of partners in crime, one from the sample that we're going to use as our best guess at what the population version is, right? So we use X bar, but really we want to learn about mu. We use S squared, but really we want to know about sigma squared, or usually for us, we're going to use the standard deviation S, right? Makes sense. If I take the square root of S squared, I get S. Cool. Versus sigma, which is the population standard deviation. Okay. Good. How's that for a review? Call that the end of our review. So today, or any questions before I start today? New, yeah. Oh, this little guy, it's like the end. I think. I actually don't know what it means. I did it sloppy now too. Kind of, I use it to indicate end of review. You know, in like old movies, and it's like the end, and then they put this fancy thing on there. That's what it's supposed to look like. Mine looks like a raggedy version of that. Anyways, end of review. All right. So, good. So we talked about the mean, the variance, the standard deviation. Those are all numerical measures of center and spread. Now, what we're going to work on today is, okay, those are actually only appropriate to use if we have a normal distribution, or at least a unimodal symmetric distribution, but let's call it a normal distribution. So that's why I saved this, okay? Because for us, right, today we're gonna focus on just unimodal distributions, one peak, okay? But then we're gonna go down here and we're gonna talk about these little guys. Okay? So if it's symmetric, we are going to call it a normal distribution. Okay? And this one is skewed to the right, this one is skewed to the left, but we're gonna lump these all into non-normal distributions because the behavior will be the same, just depending on which direction the skew is in. I think I need to add a page here. It's gonna be way too big, I think, but this. The shape of the distribution will determine the appropriate measure of center and spread. Yeah. So we'll determine the appropriate measure of center and spread. So we've got these little guys here. We're going to lump it into normal versus non-normal. Now, if you have a normal distribution, we are going to use the mean and the standard deviation. They're appropriate measures of center and spread for just the normal distribution. So if we have a normal distribution, then the center is the mean and the spread, we're going to use the standard deviation. We only introduce the variance as a gateway to the standard deviation. Now we're going to just talk about the standard deviation. Okay. That's not to say that you can't calculate the mean of this. Okay? But what's going to happen is the mean is pulled in the direction of the tail, right? And I'm pretty sure we come back to this, but I just want to point it out immediately, right? So in skewed distributions, in skewed distributions, the mean is pulled in the direction of the tail. That's all you need to know for now, right? But that makes it not a good measure of center anymore, okay? And so for skewed distributions, we're going to be talking about the median as the center. So for the center, so for non-normal distributions, the center, the appropriate measure of the center is the median, and the appropriate measure of the spread is called the interquartile range. Got a little bit of work to get up to that point, but we abbreviated IQR. And so these are the two things that we're gonna spend quite a bit of time on today, is what's the median and what's the interquartile range. The thing is, you can calculate all four of these for any distribution of numerical data. You can calculate all these things. So it's our job to know when it's appropriate to use the mean versus the median, and when it's appropriate to use the standard deviation and the interquartile range. For now, I want you to link the mean and the standard deviation in your minds, right? They're just always go together. And then the median and the IQR, they always go together, right? So they're just gonna hang out. So if you say, okay, I have a non-normal distribution, then you should be using the median and the IQR. So, like I said, way too much paper there, but that's okay. What is the median? The median is the value that splits the data in half when you've ordered it in ascending order. Okay? Meaning, okay, if you sort from smallest to largest, because I mean, technically you could sort the other way, but that's weird. If you want to, you can, but let's sort from smallest to largest, and then you have to find the middle value, and that is your median. Yeah. So I like to use my my patent pending boop 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 method, where take both my fingers and I start at the outside and then I just boop, boop, boop my way in. There are formulas and things for finding the right position, and then you still have to go find it. And for us, we're just going to be dealing with tiny data sets. And so the boop, boop, boop method will work. So here, boop, 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 bing, boop, boop, boop. Very unofficial, but if I call it a method, then that makes it real, right? I think it's the boop, boop, boop method. What if I have an even number of observations? So now, just so you can see both my fingers, boop, boop, boop. I land on 2 at the same, so 2 and 3 at the same time, right? So what I'm gonna do is I'm gonna circle those, okay? But what's gonna happen is technically the median is neither of those. It's gonna be between those two. So we indicate that with a line between them. And so here, the median is here, is this line. And the rule is, somewhat confusingly, we take the average. Now, Excel is going to use something a little bit more sophisticated. So if you're using those functions, it'll give you maybe a slightly different weighted average. But for us, right, we're just going to do it using the boop, boop, boop method. And so here, the median is 2.5, because 2 plus 3 divided by 2 is 2.5. So kind of 2 different rules depending on how many data points we have. So we can call this the 50th percentile. In general, let's see if I have a percentile. Okay, not yet. But a percentile, you might be familiar with percentiles already. The 50th percentile has 50% of the data below it, right? And so P% below this point, right? So the median splits your data in half, so you have 50% below it, therefore 50% above it, right? There's some other common percentiles that we're going to work with. The 25th percentile is also called the first quartile. Okay, I see what's going on here. The interquartile range. I don't know, if your brain works that quickly, then cool, but mine probably wouldn't. Right? But the first quartile is the 25th percentile, meaning I have the first quarter of the data below it and the top 3/4 of the data above it. We're going to denote it by Q1, okay, for the first quartile. The 50th percentile is called the median, and if you want, you could call it Q2, but it's pretty rare that we call it Q2. Okay. Second quartile, 2/4, right, is half. And then the 75th percentile is the third quartile, so Q3. Oh. So we could have something like this. If I take my data set from my minimum to my maximum, then my Q2 or my median might be here, and then my first quartile might be here, and my third quartile might be there. So I'm just splitting these into quarters instead of in half. I use the same method though, right? How did we find the median? I boop, boop, booped. Right? Now, if I want to find essentially the median between the minimum and the median, words, then that's going to be my Q1, right? So that's how we're going to find Q1 and Q3. Of course, Excel will do these, and it does it in a more sophisticated way, right? And so if you're checking your work with Excel, cool, but also just be aware that it is going to use kind of a fancier weighting mechanism than we do. We weight them all the same. I'll come back and do an example of finding the quartiles, but what we're leading up to is, okay, I want to find the interquartile range. Inter means between, right? Quartile, so, and then the range is the distance between the quartiles is the IQR, which, if you had to guess, how would you find the distance between Q1 and Q3? Most reasonably, you would take Q3 minus Q1. And so that's exactly what the interquartile range is. It's the distance between Q3 and Q1. Okay. Good. Oh, I want to add something here. I'm gonna go rogue here for a sec, but just because I want to show you an example. Let me scroll ahead and make sure I don't have one lined up, but I don't think I do. Box plots, whiskers, no. So for example, maybe not an example. We summarize the median and the quartiles using what's called a 5-number summary. We use a 5-number summary to summarize the quartiles. So the 5-number summary is going to look like this. You list your minimum, you list your Q1, you list your median, you list your Q3, and then you list your maximum. This is the 5-number summary. From way back in the day where we were supposed to use this 5-number summary in order to help us understand the distribution better. That's not how we're going to use it. I think it's a kind of a clean way of asking you to show me that you can find the quartiles, right? And so usually I say, find the 5-number summary, or give the 5-number summary of this thing. And then you're supposed to know what that is. Okay? And so we have to list them in order. The order, if you go from maximum to minimum or minimum to maximum, doesn't matter, but just make sure they're in order. Okay? And I always start with the minimum. Okay. So to find the 5-number summary, let's see here. Find the, or I guess it should be give the 5-number summary, but whatever. Find the 5-number summary of the following data. We could make up some cute thing that we've measured, but let's just grab some numbers. 2, 13, 9, 7, 12, 11, and 3. Those are good numbers. Just numbers. Okay. So first thing I need to do is I need to sort these, right, from smallest to largest. Don't forget that step. So step 1, sort. So I'm gonna have, okay, I can start with 2, but then I need to go with 3, and I'm just gonna kind of cross these out as I use them. And then I have 7, 9, 11, 12, 13. Make sure 1, 2, 3, 4, 5, 6, 7. I have 7 items here. Make sure you have 7 items before you keep going and do all that work. 1, 2, 3, 4, 5, 6, 7. So sort them, count them. Well, at your own risk, I guess you don't have to, but you do have to sort them. Okay. So now I find that from the sorted, we can answer 2 of these already, right? The minimum and the maximum. I throw those down almost immediately. So here, copy this. So I've got the minimum and the maximum, 2 and 13. I can put those down right away. Maybe I need to give myself just one more line here. That's not in here, right? It's in the other room. Wow. Crazy. All right. So a little bit more data this time, not a ton though. Right, you can probably see. So notice how I kind of space out the numbers because we are going to be counting in. And so if they're evenly spaced, it's kind of easy to see where you would land, right? But 2 and 13, boom, 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 boom. Gonna land on 9. So kind of, I land on 9, which means that 9 is my median. I'm not gonna take the average unless I land on 2 simultaneously. So then here, the median is 9. So I can jot that down. That's a pretty easy question for 3 out of the 5 things. Here's where it gets a little bit harder. I guess I should add a step 2. Do the work. Do it. There's really no step 2. Find the values. That's stupid. I just want it to have step 1 be sort the stuff and then find the values. Okay, so kind of picky rules, not because I actually care about the values so much as what I care about is, can I give you these kind of big rules and you follow them, right? Can I give you instructions and then you just take that and you follow it? And so my first stats class, my prof, who was later my supervisor for my master's, he came in and he's like, the sky is green. And then we would just have to remember all these weird facts for later, because then he would use them in questions and we'd have to remember all the rules. And so I'm not going to do that weird version of it, but kind of in a way, right? We have to remember these rules, not because, our analyses depend on it. Excel is going to do it anyways, but because I need you to be able to take rules and just follow them. Okay. So the rule, if you've used the number as the median, you don't use it to find the quartile. Okay? Which means that, okay, if I have to find the quartile, the first quartile here, first quartile is essentially the median between 2 and 9, right? It's not the median because now I'm splitting it into quarters, but it behaves the same way. And so now, because I've used 9, I can't use it to start my booping. And what's a color I haven't used? Let's use purple. And so here, my booping would start at 7, not 9. That's the rule. Them's the rules. So Q1 is 3. Not too bad. On the upper end, I do the same thing. Yeah.
Why? But isn't the quarter point between the halfway? So why is it 1 before the quarter?
It's just because we've used 9 as the median is the justification. So we'll do an example with one more where we're taking the average and then you start on that number. Yeah. Just at this point with software and stuff, it's silly, but it is something that I need to teach you. So here we are. Yeah.
Does that mean that we start from 9 or it applies to all nodes? Regardless if you ask to find median or not?
Yeah, you would still find the median and then find the quartiles, even if it doesn't ask for it. Yeah. Good. So now, same thing on the upper end. Okay, pretty reasonable. Start here, boop, boop. And Q3 must be 12. Okay. What if I want to do the same thing? So repeat, but add 5 to the data. Why not? So what I'm gonna do, oh, I should have taken a copy of this. Copy. Now I have to erase all this. Ding, ding, ding. And squeeze in 5. 2, 3, 5, 7, 9, 11, 12, 13. Why not? So now I've got one more data point. Right. I skipped the sorting, because we'd already done it. So now what we're gonna do is minimum and the maximum stay the same in this case, right? And so we can keep those here, but our median, I use green. So now I start at 2 and 13, and I boop my way in, so boop, 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 land on 7 and 9. What do? I landed on both of those, but I need one median, and so the median is 7 plus 9 divided by 2. I'm gonna go with 8. The rule is the same, just remembering that now the median is this line, which we found by 7 and 9, but 7 and 9 are no longer involved. Okay, and so now what's going to happen is to find Q1, I land on 3 and 5. And on the same Q3 must be 11 plus 12 divided by 2. I'm gonna go with 11 and a half. You can write out the 5-number summary, but instead, because I'm running out of page here, I'll write down the rule for finding the quartiles by hand, which is how you're gonna have to do it on the test, right? So if a data point is used as the median, like we did above, right? We don't use that point to find the quartiles. We do not use that point to find the quartiles. If the median is the average of 2 numbers, I'm gonna run out of space here, is the average of 2 numbers, we can use those numbers, or we use those numbers. We use those numbers to find the quartiles. As we did below. So that's the 5-number summary. It's a nice clean way of making you calculate these things, right? Find the 5-number summary, and it incorporates, you have to know what the median, well, first you have to know what the 5-number summary is, then you have to find the median, and then you have to find the quartiles, but then you also have this nice clean summary of the data. And so I feel like I skipped something. No, I just want to go back to here. So from that summary, right, you can easily find the interquartile range, which is Q3 minus Q1. We'll come back to that. I feel like I say that a lot. A box plot is going to be a numeric or a representation or a visualization of this 5-number summary. Okay? And so a box plot looks like this. It's kind of easier to start by looking at one. This thick line in the middle is where we're going to start, because that's going to be your median. Okay. Then in this case, so, or let's focus on the box first. Because of the axis that it's on, right, this bar is lower than the other. And so this must be my Q1. And then this is my Q3. So my box in the box plot just represent the central 50% of my data, right? Most of my things, or half my things in the center, are here. Then we have what's called, these are called whiskers. Cute, right? I call them whiskers. You can call them fences, but I think whiskers is cuter. But fences is what you could call them as well. Now, the rule about these whiskers is that, notice here, they seem to extend to the minimum, and they do, right? There's no points beyond here, so we can write that down. This is my minimum. But what's this guy here? It looks to me like there are points beyond this whisker, okay? And the reason that we've singled them out like this and shown them individually is because they're considered outliers. And so here, these are outliers. And there's a rule that we can use to determine if we have outliers, right? Usually if we're looking at data and we suspect that they're outliers, but now we're going to incorporate a rule that says because it's past this point, how do I find that point? That's the question, right? Then it's considered an outlier. Okay. And so here, let's call this, what color can I use? The upper whisker.
Yeah.
And then,
Yeah.
oh, hello? This is the maximum. Should I go mute everyone? I don't know. Feel like, oh, mute everyone. Okay, sure. Okay. So scary. So this is a box plot. And the main reason that we use box plots is because one, it's really hard to look at a 5-number summary and figure out what the distribution looks like. It's still difficult with a box plot, but it's easier. But the main reason we use it is to identify if there's any outliers. Okay? So here, let's see here. Try to get it on one page. So they do have a nicer looking version of what this data looks like. Yeah. One thing that I do want to say is that notice that between this point up to this whisker, or that's a bad example, between this whisker, this lower whisker and Q1 is 25% of the data, right? But then another 25 in this shorter space, which counterintuitively, I would say, means that there are more data points in that shorter span, right? So if you have a short distance, it means that you have a lot of data points there because it didn't take very long to cover 25% of your data until you move on to the next 25% of your data, right? So here it took a little longer, and then here it was pretty quick. And then here from Q3 all the way up to the minimum, it takes a long time to cover that last 25% of the data, right? But if you had to visualize this, can I do that? Oops. I'm gonna try to flip it like this. Might be more helpful. So here we have 25%, 25%, 25%, and then here 25%. If I had to guess what this looks like as a histogram on the same scale, right? I've got a lot of activity, not very much activity. Right. Nice. So you can turn the box plot into kind of a histogram if you'd like. I don't think I did it any favors here. Let's see. I'll start tapering off quicker. There we go. That makes more sense. Okay. Good. So what about these whiskers? Whiskers, we use them and we said, okay, nope, anything past this point is going to be considered an outlier, but now we need kind of rules to figure out what those outliers are or what point determines an outlier. So we're going to use what's called the 1.5 IQR rule. We're going to call it the 1.5 IQR rule. 1.5, I had someone ask me one time and said, okay, well, why not 2 or why not, 3 interquartile ranges? And there's no reason why you can't do that. It's just we use 1.5 because that's what Tukey did. And Tukey is a famous statistician, made up the box plot. It's called Tukey's box plot. And so we go with his rules. But there's no reason why you can't use 2 or 3 or something else. But we use 1.5. So the 1.5 IQR rule says that, okay, these whiskers, which are also going to determine if there's an outlier, right, are allowed to extend up to 1.5 times the interquartile range away from the quartiles. Yeah. So that means away from the quartiles is kind of the tricky part. That the upper whisker is allowed to go from Q3 up by 1.5 times the interquartile range. Now I'm going to bring in that same box plot here and try to flip it because it's just easier to think about. Let's talk about this distance here is the interquartile range. We already saw that the interquartile range is Q3 minus Q1. So we're allowed to go, so the rule says I'm allowed to go this distance, 1.5 times that distance down from Q1 or up from Q3. Okay, and that's just the rule. So down, if I've got Q1 here and Q3 here, right, I'm allowed to go down 1.5 times the interquartile range. If you hit the minimum though, you stop. Yeah. What? Yeah. I could sense it.
And that's why that graph is skewed to one side, because if it was centered, it would either be balanced, more central, if it was like So the whiskers are just kind of cutoff points. So they don't have anything to do with your data. But yes, because you don't have any dots here, then that makes it not symmetric anymore. Totally. So then you go until you reach the minimum, right? Or the whisker, or technically the point that's within the whisker, but that's too much. So then you're allowed to go up 1.5 times the interquartile range. But if you're going up from Q3, that's why it's Q3 plus 1.5 times the interquartile range. And then if you're going down from Q1, that's why it's Q1 minus, I'll highlight those, 1.5 times the interquartile range. So in this little example, from the box plot that we were given, the interquartile range is 20 minus 10. So 10 is the range here. So we're allowed to go 1.5 times 10, which is 15, up from Q3, which is 20 plus 15 is 35. Okay. And so that's why this here is at 35. And the lower whisker, from 10, we're going to go down 15, putting us at -5. But it looks like our minimum, we reached our minimum before we could get there. So that's nice. Okay. I do want to do an example, but let's see if we can get through, because these are just going to talk about outliers, and then we're going to find if there are any outliers. So any data point that's beyond these whiskers, which don't get incorporated into your data, they're just kind of cutoffs, right? Those would be considered outliers. So, okay, this is a good spot to do it. I'm gonna reuse this one because it's nice and compact. Are there any outliers in the data below? Which seems like an easy enough question, but there's actually kind of a hidden amount of work here, right? And so let's see here. I'll add a page. Where am I? So are there any outliers? Means that we're going to have to use the 1.5 IQR rule, and maybe I'll just put these guys on the same, on one page here. Ugh. First thing we need to do is we need to find the interquartile range. That's a good first step. Step 1, find the interquartile range. Now the interquartile range is Q3 minus Q1, which we said was 11.5 minus 4. Uh-oh, this math is not gonna agree with me later. Let's get it set up here. We don't just need the interquartile range, we need 1.5 times the interquartile range. So make that your step 2 maybe. Calculate 1.5 times the interquartile range. 1.5 IQR is 1.5 times 7.5. Putting me at 11.25. Which means I'm allowed to move 11.25 down from Q1 and up from Q3 and not be considered an outlier. Okay, and so now find the whiskers, or I think in my solutions, I usually call them lower and upper bounds. The lower bound, stick with that, is going to be Q1 minus 1.5 times the interquartile range. Q1 is 4, and 1.5 times the interquartile range. We already did it, so I'm going to do 11.25. 4 minus 11.25 puts me at negative 7.25. What am I going to do with that? I take my negative 7.25, and I just imagine where it would fall on this number line. So here, what I would do is draw it here, negative 7.25. So draw this on the number line. That's just to help you visualize that, okay, you can look at this. You can look at the minimum and maximum and know that, okay, I'm safe, right? But just to help you see what's going on. Okay, all my data points are within this bound, so there's no outliers on the lower end. Therefore, no outliers on the lower end. The upper bound. Upper bound, we're allowed to move from Q3 up 1.5 times the interquartile range. Q3 was 11.5. 11.5 plus 11.25, kind of sneaky there. I don't trust any math in my head. 22.75, fair enough. I'm going to take this 22.75 and draw it. It would fall somewhere here. You're really only interested relative to the other values, right? And so now, because all my data points are within these bounds, there are no outliers. Okay, so we would have looked at this data set and said, doesn't look like it, right? Kind of an even spread across the numbers. But now we have a mathematical way of saying, no, there are no outliers because all of them are within 1.5 times the interquartile range of the quartiles. Add another page. What if I do this again? I'm going to keep all these things. Oops. Copy. What if I change this to 130? Okay. There's a method to my madness here. Then if I change this to be 130, then this bar is gonna move, right? And it's gonna be here at 22.75. And then we would have an outlier. Okay. So just putting these, you don't have to put these kind of bounds on your number line, but I do think it helps you kind of visualize what's going on, right? And why you're saying there are no outliers. That's not really the point I was trying to make here, though. What was the point? What was it, Emily? Oh, yeah. If we think about the mean of the original numbers when it was 13, right? So what happens, let's say find the mean of the original numbers. Oops. That's going to be x bar is going to be 2 plus 3 plus 5 plus 7 plus 9 plus 11 plus 12 plus 13 divided by 1, 2, 3, 4, 5, 6, 7, 8. Okay. What is that? Has anyone done it? Should I do it? No one's done it. 2 plus 3 plus 5 plus 7 plus 9 plus 11 plus 12 plus 13. I get 62 divided by 8. So I get 7.75. Couple of notes here. 7.75 is pretty close to 8, which is what we found, right? What happens? Well, first, what happens to the median when I change this to 130? Nothing, right? It's just a number. And so, no, I still need to talk more. My voice says no. Right, it's just a number. And so the benefit of using the median is it says, okay, I actually don't care. I'm just here to find the middle, right? And so changing this 13 to 130 doesn't change the median, right? The median would still be 8. Okay. And so I'll say notice changing 13 to 130 does not change the median. We call it a robust statistic. Okay. And so for this reason, we call it a robust statistic. And that's the reason we use it for skewed distributions, right? Because we're going to have outliers, but we need some measure of center. Whereas, what if we did whereas the average is pulled in the direction of the outlier, which we said earlier, right at the very beginning of class, we said, okay, here's some things to know, and just know that the average or the mean is going to get pulled in the direction of the tail. And so now I'm going to show you what that looks like. So whereas the average is pulled in the direction of the outlier, which is also the tail. So if we have 130 30 now. I think I had 62 minus 13 plus 130. Now I have 179 divided by 8. Unless I did that too quickly. 22.375. Right, so it's going to get pulled in the direction of that outlier. Which is why we absolutely can calculate the average, right? We can do it, it exists, but it's not an appropriate measure of center anymore, because what if we actually looked at 22 point whatever? That's not a very good representation of where my center is of this entire data set. Right? So just some cautions. Good. So visually, what this looks like, you have a skewed distribution like this, your median kind of hangs tight, whereas your mean is going to get pulled in the direction of the tail. Okay. You can use that to figure out, okay, then what might a shape be of my distribution, right? You can compare the mean and the medians. If the mean and the median is roughly the same, it's pretty safe to assume that you at least have a symmetric distribution, right? And so then you would say, okay, it looks like I likely have a normal distribution if the mean and the median are hovering around the same place, right? Whereas if the mean is greater than the median, it means I have a distribution that's skewed to the right. And then on the flip side, right, if the mean is less than the median, I have a distribution that's skewed to the left. So we can compare the mean and median to determine an approximate shape. The distribution. That's enough of that, I think. Let's keep going. Any questions though before I do? These I'm going to skim because we already talked about robust statistics, but here it is. And I feel like I like my way of developing it better. But as you can see right here, we've got this skewed distribution. What if I gave you this distribution and I asked you, how would the median and the mean relate? Right? So then you would say, okay, well, it's skewed to the right. The median would be somewhere down here. And the mean might be somewhere up here. So then we would say the median must be less than the mean in this distribution. Which is also why it's really bad. So we've talked about, okay, a lot of money things, income is skewed to the right. Okay. And so whenever I see articles and things that talk about, you know, average household income, is that appropriate? Probably not. Hopefully they've kind of made adjustments and safeguarded, but right, we should be talking about the median household income, for example, right? Because that's a more accurate representation of the center. Same thing, you'll see articles about the average home price, Does that make sense? No. So now you can be picky and critical, just like me, when you listen to the radio and stuff. Okay. We've already spent a lot of time talking about this, but I will highlight here the median and the interquartile range, which go together, right? You're not going to split those up, are more robust to skewness and outliers than the mean and the standard deviation. Okay? And so the shape of your distribution is going to determine which center and spread to use. Hey, we already did this. Yeah, it's a nice. How about this one? Which is most likely true for the distribution of percentage of time actually spent taking notes in class versus on Facebook, Twitter, etc. I feel like it was a long time ago since anyone was on Facebook, well, or Twitter in class, but who knows? Frank is in our shared office, and it's like, I think he just discovered X, which I'm not on it because I'd get too bogged down, but he's like, it's really incredible, Emily. It's really incredible. He really likes it, I guess. You can start by nailing down the shape, right? It's a good skill to have. Well, you need it, right? Because now we know that it's going to be skewed left, which means that, okay, let's spend some time talking about the median might be somewhere here. And I'm just eyeballing it, kind of the peak of this distribution that I drew. So it's pretty arbitrary, but roughly. Right. And then our mean is going to get pulled in the direction of these outliers. So it's going to get pulled out this way. I'll make it more extreme. So if it's skewed to the left, that means that the mean is less than the median. And now, I'll give you the options now. What? Multiple choice all this time? It was. But that's how you should be solving multiple choice, right? Don't look at the answers, develop the answer, and then find the answer on here. So the mean is greater than the median. No, it's not. We already said no, it's not. The mean is roughly the same as the median. That didn't be. No, it's not, right? Because that would be for a normal distribution. The mean is less than the median. Yay! Impossible to tell. No. Don't pick that one. There are tricks that we can use if we have extremely skewed distributions. And so one of the most common transformations that we make is the log transformation, where really all we do is take the log of each of the values, and then we look at those values. And we're not really going to do any transformations or anything like that. It's just good to know that you can, and it exists. So if you have your original data like this, right, extremely skewed, then if you take, now this should say the log.
we use log base E if you're picky. Log base E, which is the natural log in stats. But confusingly, I just read it as the log because it's the only log for me, the natural log. But notice how the key takeaway is not the logs here, but it is how we can transform the shape and make it something that we can actually work with, right? And look at, right? It's hard to know what's going on here. So that's the only takeaway. So again, this should be the natural log of the games. The natural log of 70, 4.25, right? We've just taken each data point, taken the log of it, and recorded it. Okay? The problem, and the reason we don't tackle it in this course, is because it can be really difficult to interpret because the log of whatever you want to talk about is probably meaningless, right? And hard to communicate. And so that's kind of the problem with transformations is you have to now talk about the log of the number of games, which might be hard to talk about. Okay, I'm going to skip that. What other variables would you expect to be extremely skewed? I don't know, income, right? We've talked about those skewed distributions. Intensity maps or heat maps. Heat maps, I remember when they kind of hit the scene in the way where it became really easy to make heat maps. And so then everyone was doing it because it used to be really difficult. And now all of a sudden it was really easy. And so everyone was doing heat maps or intensity maps, but we use them a lot, right? Newspapers and things like that. And so we've got kind of a legend of what each color means and kind of hotter here. Hotter meaning a decline in this case. I don't know if I would have used those colors, but anyways, doesn't matter. And then colder down here, which means you have an increase in the populations. Probably would have switched the color schemes, but that's data biz, data visualization. Okay, just an example of how you could visualize numerical data. Okay, let's do it. Any questions before we do? So categorical data is not that exciting. There's not a lot that we can do with categorical data, not nearly as much as we can do with numerical data, right? And so categorical data usually is summarized in some sort of contingency table or a table, right? And so a contingency table, we're just jumping right into it, is for two categorical variables. And so we might have the gender and whether they're looking for a spouse, yes or no. Relatively basic table here, but our job will be to read this table and pull out the appropriate numbers. Yeah. What does this 86 mean? Means that in our sample of how many? 207. Right. In our sample of 207 students, I guess, 86 were female and not looking for a spouse. So of our sample of 207 students, 86 were female. And I'm going to highlight that and not looking for a spouse. Why did I highlight that and? Because how many were female? 137 out of the 207 were female, right? Regardless of whether they were looking for a spouse or not. Same idea. How many students were looking for a spouse? Running out of colors here. 69 students were, I should really looking for a spouse. Make this a less weird example, but I forgot to change it last year and I'll probably forget to change it this year and I'll keep using it till one day I'll remember. Okay, so reading contingency tables, right? Thinking outside the bun here. What proportion of males were not looking for a spouse? So let's consider this. What proportion of males were not looking for a spouse? One step further, or like 3 steps further, but I think we can handle it. Or at least it's good to see it. Because now, instead of the total being 207, I'm really just interested in, of these 70 males, how many were not looking for a spouse? 52 of those 70, right? And so my proportion is going to be 52 over 70. Notice that I changed the total because I'm only talking about the males. Okay. Which you can easily convert to a decimal. What is it? 52 divided by 70 is roughly 0.7428. I'll round to 6 hertz. Or our minds automatically make them percentages, and that's what's cool about percentages. 74.286%. All of these are the same. Okay. In fact, all these proportions, percentages. So a proportion is almost a percentage, but it is a probability. Right? We'll do that in the next chapter, probabilities, but that's what we're going to be working with, right, is probabilities. And so we use all these P words somewhat interchangeably, right? I have roughly the percentage because I need to multiply by 100, but our minds just do that for us, right? So I'm equating them basically. But a probability is a proportion, which we can easily convert to a percentage.
So you can use those interchangeably. All right, but I've derailed. To visualize categorical data, we use bar plots. I'll say to best, because there are others, visualize categorical data, we use bar plots. Bar plots are exactly what you think they are. They're bars representing the count in each category. So for example, you can have the raw count or the frequency plot, or you can convert them to percentages or proportions and have the relative frequency. Notice that the shape doesn't change, right? You're just shrinking one down, putting it on a scale of 0 to 0.6 instead of 0 to 120. But so the information that you get out of it stays the same, but it is a little bit nicer to have the relative frequency. How are these different than histograms? Well, now I have these categories on the x-axis, whereas for histograms, we had numerical data. So then I had a number line that I just put my bars on, right? We can talk about, we can look at these numbers and determine if we suspect that there's some sort of relationship. So for example, does there appear to be a relationship between gender and whether the student is looking for a spouse in college? Now, what we can do is we can look at the percentage of females. So now the total is the females, right, who are looking for a spouse is 51 over 137. So roughly 37%. Percentage of males that were looking for a spouse, 18 over 70, which is roughly 26. Now, this is where it kind of becomes a judgment call. Do you think that 26% and 37% is roughly the same, or are they different? I would probably lean towards slightly different. Okay. Do I have? No. Since 37% is, I hate to use the word significantly more, because that's going to be a special word for us. But if I say it now, will you forget that I said it later? How about this? I know how to please us both. Since 37% can be considered significantly more than 26%, huh? How's that for a loophole? And 26%, we suspect that there is a relationship. We suspect is a relationship between gender and looking for spouse. On the flip side, right, if they're essentially the same, right, then knowing the gender doesn't tell you if they're looking for a spouse, which means that there's no relationship there. Right? Nice. If we have two variables, so we looked at a bar plot with just the one categorical variable, right, male, female. Now if we look at bar plots with two variables, we have a couple of options. It's not important to me which one you prefer, but a stacked bar plot is the bars are stacked. We can have side-by-side bar plot, then you take them apart and you put them beside each other. And then a standardized stacked bar plot is on a 0 to 1 scale. Now I'm really hoping, there we go. Okay. Here's a stacked bar plot. What's the difference between this stacked bar plot and this stacked bar plot? Well, it's going to be the scale. So it's been standardized on a 0 to 1 scale. I think it was called standardized. And this is a mosaic plot, which I don't care about. Or is it? It's not a side-by-side box plot. It is a mosaic plot. I'm not going to use those. I don't like them. What's it doing? The width of the bars means something, right? And so that's why I don't like that, because that's hard for our brains to kind of handle. There. Another example. This is from the Titanic data set, which we use often to illustrate categorical data, right? Did they survive or did they die? Were they an adult or a child? Now, of course, there were many, many adults on the Titanic and not very many children. But of the children, it looks like a slightly higher proportion survived. So, cool. Pie charts. We never use pie charts. It's tempting, I know, but pie charts are, it is a way that we can visualize categorical data, but it's not very useful. And so we should avoid using pie charts. One of the reasons is, well, this is an extreme version of it, but can you tell which order encompasses the lowest percentage of mammal species? So we understand how to read this pie chart. That's a nice thing about a pie chart. You're looking for the smallest slice, and I don't know, I can't see it, right? This is an extreme example. But if we have bars, it's easy for our eyes to see which bar is the highest and which one is the lowest and how they kind of rank. And so versus a bar chart, here I'll say hard to see. A bar chart, I'm not going to draw all those categories, but even if you have a bar like this and a bar like this, those pies or those slices of pie would be very, very similar, right? But it's easy to see that, okay, this one is just slightly less, right? And so it's easier for our eyes to read it. Note. The whole idea, or the main idea with data visualization, is that it should be easy to gather information, right? You shouldn't have to read a legend, and you shouldn't, or unless it's absolutely necessary, right? You shouldn't have to kind of figure out what's happening
right? And so data visualization should be as easy to interpret as possible. I've been down that rabbit hole. I've made, you know, some very nice visualizations, but then I go to show it to a coworker and they're like, so what does this mean? And I'm like, oh, well, that means that. And oh, and what does this mean? Well, it means this and this. So as soon as you have to explain what's going on, it's probably not a good data visualization. Okay. Let me just scroll ahead. Okay. One more slide. So we can do it. Okay. So I don't want to see you say pie chart when I ask you, how would you visualize this variable? If you've determined it's a categorical variable, the best way to visualize it is with a bar chart, and not a pie chart. It'll be one of the options, but it's wrong. There, I told you. What about numerical data? So now we're back to numerical data just briefly for one slide. Across groups, which is across categories. We're going to use side-by-side box plots. Isn't something that we're going to make by hand or anything, but in Excel, it's relatively easy to have it generate side-by-side box plots. And I'll post our first Excel assignment for you to get some practice with Excel. And if you haven't downloaded your Office from the college, because you get it from the college, well, in your tuition, then make sure that you do that, because we'll be using Excel for some of the assignments. Okay, but that's not on the tests, just by hand on the tests. So now we've got the numerical scale on the y-axis, and then we've got our categories. So we've split up our numerical data into these groups: first year, sophomore, junior, senior. Those don't mean anything to me, but means something. And one day I'll learn. Presumably it's in this order. Why? Because it's ordinal data. It would make sense to have them in order. First year, fine, should come first probably. Then I guess you're a sophomore, is that true? Does anyone know? Are we all just lost? And then you're a junior? And then you're a senior? Is that true? Anyways, that's how I read it. Because it's ordinal data, right? The categories have natural ordering. So presumably that's the order. All right. That is the end of chapter 2. So we'll pick up in chapter 3 on Thursday. If you have any questions, let me know. Otherwise, see you then. Thanks.